Good evening, good morning, wherever you are from. So let us welcome Professor René de Koster, our speaker for tonight or today. Professor de Koster is a professor of logistics and operations management at the Rotterdam School of Management at the Erasmus University. And he also chairs the Department of Technology and Operations Management there. He holds a PhD from Eindhoven, University of Technology. He has received many awards and honors, including the 2018 Honorary Frankie Professor at the Hasselt University. His research interests are warehousing, material handling, and behavioral operations. He's a founder also of the Material Handling Forum at Erasmus and is author editor of 8 books and over 240 papers in books and academic journals. He's associate editor of very well-known informs journals such as Transportation Science, Service Science, and Operations Research. Before giving the floor to René, just let us quickly introduce to this webinar. TSL is a Transportation Science and Logistics is a special interest group within the overall informs community. We have different verticals like urban freight, facility logistics, intelligent transport, and many others. Today's talk is particularly focused on the facility logistics SIG community within the umbrella of TSL. And we usually have one such webinar every month under the leadership of Mike. So without much delay, let us welcome Professor René de Koster. He'll be talking about the Cobotic order fulfillment systems, which is getting more and more popular as we talk about it. Welcome, René.
Thank you very much, Debjit. Just a question, can everyone see my screen, my presentation?
Yes, we can.
Great, then I can continue. So indeed, my talk is about Cobotic order picking systems. And well, I explain to you what these systems look like. Before I start, maybe first some introduction about what many people have the idea of what robotic picking and robotic warehousing would look like. Something like this, maybe.
And we've been saying, how close to human levels of performance and speed could we get in an ordinary task like moving boxes around on a conveyor? And we're getting up to about 2/3 of the speed that a human operates on average. And this robot is using both hands, it's using its body, it's stepping. So it's really an example of dynamic stability, mobile manipulation, and mobile perception. Here, we actually have two atlases. Now, everything doesn't go exactly the way it's supposed to. And we've been saying,
So this is not like how most robotic warehouses look like. They are really different. But it is good to have this as a perspective of what might be a future. So if you look behind the screens, well, there are all kinds of systems that help you in fulfilling your order. If you order something online, you're sitting behind your computer, behind your cell phone, and you type in some order, then in the background, these orders have to be picked somewhere in a warehouse, have to be packed and then shipped to you. And doing that work is, well, it's really a lot of work in many cases. And of course, we want to have this done fast, at low cost, high quality, and preferably also in a safe way and flexibly. So this is how it's done in a manual operation. There's a lot of people doing all that work. And on the right side picture, you see there's a lot of orders waiting to be shipped there. And it involves a lot of walking, an awful lot of walking. These warehouses are really big. They host a huge number of products. And in order to retrieve all these orders from these shelves, large walking distances are required. So it would be nice if we could automate this. And one of the automation ideas would be to robotize it. Well, if you think of robotization, this talk is about cobotic systems. So basically robots and people working together. But indeed, you might go one step beyond and think of fully robotic operations. And in fact, fully robotic warehouses already exist. So what do they look like? Well, here I have a couple of examples of warehouses that are fully robotic, meaning very few people are involved. This is one of the oldest, a wholesaler in Germany. This is Coop in Norway. This is a grocery retail chain warehouse. They have different temperature zones, and each of these temperature zones has its own robotic automated system, and all these orders then come together to be shipped in the same truck to the store. Fully automated. This is a warehouse in the Netherlands of Albert Heijn, operational last year, also fully robotic. And this is also in China. We have fully automated warehouses. This is the warehouse of JD.com, an e-commerce retailer. And you also find them in the US and in other parts of the world. So now more and more warehouses have become fully robotic. So how do these warehouses work? How do they operate? Well, this is a schematic flowchart of all the processes you find in such a warehouse. So we see trucks coming in, goods are offloaded, then the pallets are stored in an automated fashion, then they are destacked automatically by robots, then the boxes go into a different storage system where every box can be handled individually. And when the order hits the warehouse, the boxes are retrieved, sequenced in the right sequence desired by the customer, and then built on a pallet, and a mixed pallet, exactly in the way the store wants to have it. So this is particularly the process for store-based warehouses. Finished goods go into a buffer until the truck arrives. They automatically are taken off the buffer and loaded into the trailer. And they might even be sorted using a robotic sorting system. So these are fully automated warehouses. So why am I talking about warehouses where robots collaborate with people? Because, well, apparently in these types of warehouses, it's not needed. By the way, this is the major innovation that has made these automated warehouses possible. It's mixed a roll cage and mixed palletizing in a fully automatic and fast fashion. So this is really the big revolution of the last 10 years. However, if you look at these warehouses, they are extremely expensive. So you have to think of many millions of dollars in order to pay for these warehouses. And that basically means they're not applicable very broadly. So you find them primarily in store-based retail, particularly grocery retail, where you might say the coming years of sales are secured. You have long payback times if they will pay back ever. And usually there are other reasons why these warehouses want to have fully robotic operations. The reasons not being cost reduction, but the reasons being we want to work 24/7, and we cannot find the people to do the work 24/7. And in order to keep on working, these warehouses start introducing robotic systems to be able to work around the clock. Okay, so my talk is not about these fully robotic warehouses. It's about a particular system. And here you see all these automated systems that you might deploy in your warehouse. Here in the left top corner, you see classic automated systems. They are around already since long. And all the gray shaded things are robotic type of systems. And I'm only going to talk about a very small niche here, the lower right corner. Collaborative robots. Robots working together with people in a picker two parts type fashion. So only a very small part, but I think a very important part, which has not received a lot of attention. So I'll explain why this is such an interesting area to study. And I do that based on 3 research projects related to these systems that I'll go over with different studying different aspects and also using different methodologies. So my topic is Cobot, collaborative robot, AMR systems, and AMR stands for Autonomous Mobile Robots. So if you look at these cobot systems, they basically bridge the world between automated and manual systems. If you look at automated systems, fully automated, yes, they are great for throughput performance, but they are really, really expensive and also not very flexible. So you have to invest in systems, not only in the robots, but the whole system around it. And typically you also have to look into the layout of the warehouse. It might require even special racking, like the Amazon robotics warehouses. The racks are there mobile, so you require specific racking. Whereas the manual systems, well, they're easy to implement. They're very flexible. No special investments or high investments are required, but unfortunately, they don't have a too high throughput. So the throughput is in general lower than what you can achieve with automation. So collaborative systems basically bridge these two systems, and they have a bit of advantages of both. So there are three basic variants of these systems. First, number A, you see a picker with a headset, and you see a small robot. So in this case, the picker is in the lead. He or she reads instructions from the computer via the headset. And he or she walks to the location, picks something, and the robot follows the picker like a dog. So the picker is in the lead. You can also have systems where the robot is in the lead on the right over here. So here the robot has a display and tells the picker, I'm here at this location, pick this product in this quantity and put it in a tote. And then you have other systems where the robot can also be ridden on by the picker. So the picker drives the robot, rides the robot, and when the picker arrives at the pick location, he or she gets off the robot, and then the robot starts following the picker. So it's a hybrid. You can drive it, but you can also use it as a robot. So these three systems, that's what I want to discuss. And these systems have become really, really popular, all these different variants. So there are many suppliers in the market. So here you see some names and some systems. This is by no means, this is complete. It's just a list, and here you see some photos of implementations of these systems. So you see big trucks, like over here, this is a bigger truck. You see the small robots where you walk. So you can have big trucks for driving, and you have small trucks for walking. And also the human leading, and where the robot is leading, the cobot is leading. There are different suppliers that support these types of operations. There's also a third way of operating, that's one picker working with multiple robots, and also one robot can work with multiple pickers. So, and I give an example of that in zone picking. So let me start first with the top two types of operation. So we walk together with the robot, and the robot can be in the lead or the picker can be in the lead, but we walk together. So how does that work? Well, this is the way it works. The robot goes to a location, and the picker receives instruction to also go to that location. And starting at the first location, they pick something, and then they travel the warehouse to pick the complete route together, the complete order together in a route. And when the last item of that order has been picked, the robot goes to the depot with the collected items, and the picker is then matched with the next robot and continues with the next route. And hopefully the picker doesn't have to wait too long for the robot to arrive, because we want to use the pickers as efficiently as possible. So if you look at these systems, they have quite a few benefits. So these are some pictures of these systems. And the benefits are as follows. Sorry for the typo. First one, by operating in this way, we can reduce the walking of the picker. The picker does not have to go to the depot every time an order is complete to drop off the order, or to collect a new empty roll cage or a pick cart or something. The picker can just be productive and pick all the time. So pickers are more productive. The second one is they're very easy to implement. So if you have an existing operation, you don't have to rebuild your warehouse. You don't have to tear down racks or anything. You just implement it in the current operation. And you can even have a parallel operations. Pickers completely working manually with a pick cart versus pickers working together with a AMR, with a robot. So you can have both mixed. And that also means that you can gradually grow with your volume. So you can introduce these systems, these robots over time. If you have more volume, you can afford to have more of these robots. So it's an easy invest and also an easy fallback. If it fails, you just keep on working manually, no problem. And it's also safe. So little risk of accidents. So it's quite an interesting system. You might say this is sort of the poor man's robot. No big investments needed. We just invest as we have the volume available. So this is an example of an implementation. This is locust robots. You see the small robots is waiting for a picker. So the picker comes to a robot and then picks, and then the picker continues, in this case, with another robot. So how good are these systems? How well do they perform? Well, that's one question. We wanted to study that, but particularly we were also interested to study how they work together and in a different organization, in a zoning system or in a no zoning system. So let me explain you what that is. If you have a no zoning system, basically one picker travels in the entire warehouse with the robot. However, you can also zone the warehouse, called that progressive zoning, and that means you make the travel distances for the workers smaller. Every worker is confined to one area of the warehouse, the blue area or the green area. So when a picker is done with the last item in the blue area, the order might not be complete. So the robot then continues to the green zone and is matched with another picker, and they continue the order in the second zone. So this picker only travels in the blue area, and this picker travels only in the green area. So shorter travel distances. Now there are also performance trade-offs with these systems. If you have no zones, basically meaning you have a large zone, you work in parallel, then basically the picker has to travel longer distances, taking more time. But robots will have to wait shorter for pickers because there's no handover. That's exactly the issue with the progressive zoning system. A robot in the green zone will have to wait for a new picker. So the robots will wait longer. So there is some trade-off here if you look at total time. So our research question is, does it pay off to switch between zones depending on your order portfolio? And now that might seem as a bit of an odd question to study, but basically this is something that has become possible only with this system. In the past, it was not possible to switch between a no zoning and a zoning system. And the reason is that typical zoning systems are implemented in hardware, in conveyors with pick stations. And you cannot just say, well, I now remove all the pick stations and I just have a different zoning structure. But with these robots, everything is completely flexible. So this is possible. And I want to show to you that it might indeed be interesting to sometimes have zoning and sometimes have no zoning. So in order to study the impact of switching, we use the following type of model. First, we should be able, for a given strategy, to estimate the performance of that system. And then we can use, for that we use a queuing network modeling tool. So the queuing network modeling tool is able to estimate the performance of, for example, the throughput capacity of the system for a given strategy. And then we can use that in a Markov decision problem in order to determine when should we switch between zoning or no zoning. That's the idea. So there are two stages. First, we estimate the performance, particularly the throughput capacity, using a queuing network model. And second, we deploy that knowledge in a Markov decision problem in order to determine what is the optimal switch moment and what does it bring. Of course, we have a number of assumptions. So like uniform storage, the robot seizes the first available picker. Robots can overtake each other. We assume the picker dwells at the last position and is then matched with another robot. The pick routes are S-shaped routes. So basically we move in an S-shaped curve, like a snake curve from left to right, and then we move from right to left the next tour. but the model basically allows different routes. And there's only one I/O location. So let's look at the model. The first thing we have to do is we have to model the movement of the robot and the picker to the first pick location. And the picker can only start when the robot is there, and the robot, of course, has to wait for the picker. So only from that moment on, they start working together. So then they pick the items together. So we have to carefully model this part. And we also have to model the part where the robot goes to the depot and the picker is matched with the next robot. So we do that using a queuing model. It looks like this. So the first part is when the picker travels from his idle location, from the dwell point to the first pick location. And at that location, well, they also have to wait for the robot because both have to be there before the picking process can start. When the picking process is finished, the loaded robot moves to the depot and there becomes empty again, and then it's available. So robots circulate in this part of the process. So this is particularly the difficult part. How can you model this part plus the fact that both has to be present before the picking process can start? So we do that using a two-phase server. So basically this picker travel from the idle location to the first pick location and then waiting there until the robot is there so we can start the next process. That's modeled with a two-phase server. So the first part is basically the time that is needed for both to travel to the first location and both to be present. And only then the second part can start. So the second part, that's this part, we pick in a certain routing strategy and we make sure that all the items have to be collected. So what does it look like? We have here this two-phase server to model the travel from the idle location to the first location, to model the merge of the two systems, the synchronization of the two systems, and then the pick process. This is another queue. So the robots queue at the depot. And in between, we have just travel time, which is modeled as an infinite server. And here we have a queuing network. So this is the network with only one picker. Of course, you can also do this for multiple pickers, and you have parallel pickers here. So you can do the same. And you get a different model for the no zoning situation than for the two zone situation. So the two zone situation, here you see, this is the pickers in zone 1, this is the pick process in zone 2, and we can switch from zone 1 to, well, we can shortcut, we immediately move back, or we can go from zone 1 to zone 2. So there are different options here, different routes are possible. The robots can move. When the order is completely finished, they immediately go to the depot. But if an order needs picks in both zones, the robots have to move from zone 1 to zone 2. So the robots basically move in both zones depending on the order composition. So a different type of network is the result. So how do we solve this? Well, this is a rather simple network. You can solve the continuous time Markov chain completely. And for this more complicated network, we have to use an disaggregation technique. So this is approximate, but fairly accurate. And of course, you can extend this from one zone to two zones to, well, whatever zones you want. But of course, the routing becomes more and more complicated. So too many zones is quite a challenge, to be honest. So let's see how good this method is. So how good quality are the outcomes compared to, let's say, simulation. So in this case, we have a warehouse which consists of two blocks, a top block and a bottom block. And here what you see is the depot is in the lower left corners, and the items that need picking are the dark black dots, dark black squares. So we assume that the order picker with the robots travel in an S-shaped curve, and we first do the top block and then we do the bottom block. In this case, if there's only one zone. If there's two zones, then you would do this per zone. So we assume here 20 aisles, 20 storage columns per block, 3 cross aisles, so here at the front part, in the middle, and at the end, 6 pickers, and here are some speed data. So what is the result? Well, What we do is we vary the number of robots from 2 to 10. We also vary the handling time in the depot, and the number of pickers is, in this case, 2. So we have more robots than, so we have 6 pickers. These are the results for only 2 pickers, sorry. But we vary the number of robots. So here are the results. This is the mean absolute percentage error, and we see that in throughput, the error is really small compared to simulation. And the maximum percentage error in throughput is only 3%. And the minimum error is about 0.72%. We also see that the utilizations errors are even smaller. So the throughput errors are up to 1.96% on average, at least, and the utilization errors are a bit smaller. So it's quite good, at least good enough for further evaluation. So let me come back to what is the best policy in different circumstances. So here I have a chart, and here we compare 2 different policies. We compare the no zoning policy with the progressive zoning policy. And what you see in this graph is on the vertical axis, the order size in the warehouse, and here the number of robots in the warehouse. So what you see is, you see here, what is the improvement of one over the other? So for example, this means that no zoning in this particular case, so with 8 robots and order sizes of 10 locations, no zoning is 12% better, meaning 12% higher throughput capacity than progressive zoning. However, if the order sizes are small, we see that typically progressive zoning is better. And this is obvious. If you have really small orders, it's good to split your warehouse in zones so that you prevent pickers from walking very long distances. So it's good to divide the warehouse in zones. So that's what you see here. Small orders, use zoning. Large orders, no zoning. We also see that it's also impacted by the number of robots we have. So if we have more robots, then we see that the order size should be larger in order to benefit of no zoning. So these are some general conclusions. Large orders, no zoning. Small orders, progressive zoning is better. However, the question is, does it now also help to switch between these 2 strategies? Assume that you have a mixed order pattern, for example. Let's assume that we have both large and small orders and they come in at certain rates, depending on what I have in portfolio. Would it help to switch? And for that, we use the Markov decision model. So what does it look like? Well, here we have as a green box, we have the queuing network evaluation of a certain policy. For example, no zoning or progressive zoning. And what we use the Markov decision process for is to decide, should we switch? In order to do that, we have to define costs in a certain state. So we distinguish here different types of costs. We distinguish waiting costs of orders, because in these types of environments, you want to handle things very rapidly. So we attribute a cost if an order has to wait for service. And we also, if there are too many orders, we have to postpone an order to the next day. So we have a maximum capacity of the system. And beyond that, if more orders arrive, we just have to delay them. And there's a postponement cost involved in that. So these are the 2 types of cost. So for a switching policy, we have to decide when should we switch. And we do that based on the state of the system. And the decision epochs are exactly when an order arrives, a new order comes in, then we take a potential decision, no change or change. And we also take a potential decision when the order leaves the system. And this is the state space we assume. So we have a 3-dimensional state space with the number of small size orders that we have in the system, the number of large size orders, and the number of zones. So with 1 zone, we have no zoning, a pooled system, and with 2 zones, we have a system with progressive zoning. We also have an action space, and action is quite simple. Based on the state of the system, we can decide to maintain as is, or we can change to the other type. So from no zoning, we go to zoning, And from zoning, we go to no zoning. That's a change. So let's look at the arrival rate or the rate of moving out of state S. This depends on the arrival rate of orders, but also on the departure rate, the finishing rate at which we finish an order in the system. So this is the arrivals of orders in that state, depending on the state. And this is departure from that state when an order is finished. And of course, this service rate, that depends on what we found in the queuing network model. So the queuing network model determines the speed at which we are able to finish order. It's basically the throughput capacity of that system. And that's determined using the queuing network. Okay, so all the tools are now in place. We just have to determine the total cost function. So this is the total cost function in state S. So it consists of a number of elements. It consists of waiting cost, it consists of postponement cost, and we might also have additional switching cost. And we look at the average expected cost per time unit. So we don't look at the discounted cost, we would just look at average expected cost. So how do you solve this? Well, you can solve this using a policy iteration. Then you find the optimal switching policy. So for every state, we know now, should we switch or should we not? So we just developed the Bellman function, and you can solve that for this particular case. So let me give you an example of what it might bring. So this is a warehouse of DHL. We have, so it's again the same warehouse. These are the data, 6 pickers, 2 blocks. The picker speeds, we have here the costs of waiting, postponement, and switching. You see we have quite large postponement cost. If we have to tell a customer that the order is delayed, well, we attribute quite high cost to that. And switching costs are relatively low. So what comes out? So this is the case for 8 different robots, and we assume in this case that the percentage of small orders is 55%. So these are the states of the system. We can have maximum 20 orders in the system. So they can be either large, or they can be small, or they can be a combination of large plus small. So what we see is that if the number of large orders dominates, and we are currently in a no zoning situation, we should stay there. No change. However, if you are currently in a no zoning situation and the number of orders the number of small orders becomes larger, then the system tells you you should change from a no zoning situation to a zoning situation. So this is exactly what we expected. So sometimes you should sit where you are, but sometimes it's good to change. And it depends on the current strategy. And of course, if your current strategy is progressive zoning, you might switch to the other one, just the other way around, particularly when the number of orders number of large order becomes large, then you have to change if you currently have a zoning system, meaning you should go to no zoning. Let the picker do everything if the orders are large that you have to do. Okay, so the optimal strategy is, yes, you should sometimes change. But the question, of course, is, so what? What does this bring? And in order to do that, we compare the different strategies. So we assume that we have a strategy of no zoning all the time. We have a strategy of zoning all the time. And we also have the optimal switching policy. We switch depending on the portfolio. And we just compare these 3 different strategies using a simulation. So we simulate this network, and we have different decisions whether depending on our policy, do we have no zoning or progressive zoning, or do we have a switching policy? So we have to use different service rates depending on the queuing network that we just developed. So the queuing network will inform us about the service rates in that particular case, assuming that we are working on a small order, mu1, or a large order, mu2. So we have 4 different service rates derived from the queuing network, and we know the optimal policy. We simulate and we compare these 3 policies: optimal switching, constantly no zoning, or permanently zoning. So this is the result that comes out of it. So what we see is, in this case, for example, for 8 robots, on the horizontal axis, the probability of small orders, so the percentage of small orders. And here you see the cost benefit of the switching policy over the other two. So for example, this line means that progressive zoning is 10% worse than the optimal switching policy. But you see that progressive zoning indeed can be as good as the switching policy when the number of orders when the orders become very small. When you have many small orders, then progressive zoning is as good as the optimal switching policy. So in region A, you might say, well, the no zoning policy, we have mostly large orders. The no zoning policy is as good as the optimal switching policy. And in region C, we see that the progressive zoning policy is as good as the optimal switching policy. But in between, there's a range where basically the optimal switching policy is better than both. So indeed, there is a region where it's very good to switch. And this is particularly the region where you have both small and large order. You might think of an omni-channel warehouse. In omni-channel warehouses, for example, we have store orders on one hand, but we also have e-commerce orders on the other hand, and we have to do both. We have a mix. So particularly in those environments, it pays off to have a switching policy. So we obtain lower costs. So that's basically the crux. Yes, indeed, this pays off. And this is one of the very few systems where you can really have this dynamic zoning ID. So we were really thrilled with that result. Many companies either go for zoning or no zoning, but here you can basically do the best of both. And it pays off depending on your order portfolio. So conclusion of this part is, yes, cobot order picking system can improve productivity. Even dynamic switching can help. However, of course, there are a lot of questions that are still to be answered. And one of the big issues that we were facing is, but how do people really work with these systems? To what extent does the performance not only depend on the way you operate it, but also on how the people work with it? So we did some other research in order to look particularly into the behavioral aspects, the human.
René, there is one quick clarification. Would you like to take it at this point?
Sure.
The question is, what is the current bottleneck to mass adoption of this Cobotic picking system?
To what? To mass?
Adoption. So why are not people adopting this in masses? What is the current bottleneck for that?
Well, to start with, it's really new. So I think the adoption will still come. To be honest, I think this is not an extremely attractive system because the robots are still expensive. And you need more robots than people had. So you don't want the people to starve. So you need to have a ratio of about 1.3 robots at least, and preferably with more per order picker. So it pays off if you have multiple shifts. If you also have to fill orders in let's say late hours when it's very hard to find people. And there's another type of cobotic system, I come to that later, which is really adopted now in a very rapid pace.
There's a follow-up question also, like what are the advantages of this cobotic system in comparison to the popular Kiva-based system?
They're a lot cheaper.
Okay.
Kiva is very expensive to overhaul your complete warehouse. And then you might wonder, is Kiva the best? Because Kiva is just a man-to-good system. Sorry, a goods-to-man system, parts-to-picker system. There are many competitors to parts-to-picker systems, many. And the question is, what is good for you? So Kiva is good for some, but not necessarily good for everyone. And so you have to look at, there are at least 20, 30 different types of systems that you can select from in parts-to-picker.
Sure, René.
Yeah, so this is picker to parts. And picker to parts, well, you can implement as you go. So we'll see more implementations in the future. At least that's what I think. But good, let's look at the role of humans. First, you can work differently with these systems. So I showed you two pictures, one where the human is leading and the other one is where the robot is leading, the cobot is leading. And this might lead to different performance. In the model, it doesn't make any difference, but in reality, there might be a difference between these two ways of operating. The second question we might have is, does it matter what the personality trait or the behavioral trait of the person is, what the performance will be? So that's the second question. And we particularly looked at prevention focus of the workers and to what extent it will impact performance. And the third aspect has to do more with the person, him or herself. So how will it affect the worker's psychosynthesis? That's the third question. So this paper is work with Alexandros Pasparakis and Jelle de Vries, and also this one is still a working paper. So here is the three things we want to investigate. Does the treatment human leading versus the human supporting or the robot leading have an impact on productivity, but also on accuracy? The second one, does the prevention regulatory focus of the worker have an impact on the productivity? And the third one, is there also an impact on variables like the satisfaction of the worker with the task, the self-esteem of the worker, and how the worker thinks about the efficacy of the robots? So there might be effects on these variables as well. So I want to start with this. Is there an impact on productivity and accuracy? So we have two systems, the human leading versus the human supporting. And well, there is some literature on that, but given time, I don't want to extend too much on that. Let me just show you two short videos of that. So the left-hand side, we see the human leading. So in this case, the picker has a wrist terminal, and the terminal tells the picker where he or she should go and what he or she should pick at that location. The robot just follows the picker, and the picker drops off the item in an order bin. In the right video, we see that the robot is leading, and the robot has a screen mounted on it, and the screen is just an iPad in this case, tells the picker where the robot is going, and at the location what the picker should pick. The location, quantity, and the product description, and when done, the picker has to confirm by hitting the keyboard by hitting the screen on the robot. So you can already see there looks like a bit of difference in attitude between the two different people, although they're the same people, the same persons. But it looks like the right one is behaving differently than the left one. So everything else is the same, the speeds are the same, the products are the same, the orders are the same, but still there might be a difference. Although in our model, we assumed everything is independent of human leading or human supporting. So if you look at the variables that might affect the performance, well, we have to look at a number of things. For example, we have to look at the competence of the worker and the experience of the worker. So we use these as controls in an experiment. And we also measure the regulatory focus, particularly the prevention focus of the worker. So the prevention focus is basically a behavioral trait which tells how people try to achieve their goals in work. And there are two variants of that. You might say people are more promotion focused, they directly go for their goals, or they are more prevention focused. And when they are prevention focused, they try to go for the goal by circumventing, you might say, difficulties that divert them from achieving the goal. So people can have both promotion and prevention focus in a certain balance. But we particularly looked at what is the impact of people who are more prevention focused on performance if they work together with a robot. So we did that in an experiment. So here you see the layout, and the warehouse that we erected was with the help of these companies. So we had some help in order to erect this warehouse. This is what the warehouse looks like. So it consists of 2.5 aisles, 300 pick locations, and we had participants who had to pick orders together with a robot. And the task was pick as many lines, correct lines, as possible within a certain time limit of 20 minutes. Had some incentives, so we had a fixed monetary compensation with a productivity bonus and a prize for the top pickers. And they also received a certificate of training. So we did this experiment with vocational students who were trained to become logistics professionals. So these are the warehouse workers of the future who really will have to work with these types of systems. So we did not use university students to do this. So we had two robots, robot 1 and robot 2, so that the picker would never starve. This is the setup of the experiment. So 2 phases, 3 different rounds of physical picking with some instructions before and some questionnaire that they had to fill out. So we had a first round of manual picking of 20 minutes to basically determine the pace at which this worker was able to pick the orders. And then we had two different runs in a random sequence, one where the picker was leading and the second one where the robot was leading. Also 20 minutes, similar order sets. So we used 3 main order sets and we also randomized that and controlled for the sequence of the order sets. So this is the result on productivity, total productivity. And this is a linear mixed effects model because obviously the results are nested by subject. So we have to account for that and we use linear mixed effect model to do that. So what you see is, so here you see the controls. So this is the competence level of the order picker, more competence, higher productivity, obviously. Here are the controls for the different order sets, controls for order picking experience. So not too big effects, not significant, but the human leading compared to the other scenario where the robot is leading has a big effect. So you see that when the robot is leading, you see there's effect of 5 lines on per 20 minutes on the productivity. So that's a substantial impact. So when the human is leading, it's really superior compared to the robot leading, which is the base level in this case, in total productivity. So even when the robot has the same speed, controlling for all the other effects, still when the human is leading, we have a higher productivity. That's interesting. So we should not have the robot leading, right? That's the conclusion. Unfortunately, that's not 100% right, because if you look at the accuracy, and in this case we measured errors, so it's inaccuracy that we measure using a binomial mixed effect model, we see that when the human is leading, we also have more errors picked per 20 minutes. So this is not wanted, obviously. So the human leading is better for productivity. Unfortunately, there's a trade-off with pick errors. So we also have more errors when the human is leading. So for that, we should have the robot leading. Okay, so mixed conclusions. You can also look at the interaction effect. So of the effect, what is the effect of prevention focus of the worker? And here you see the effect on productivity in this interaction plot. You see 2 graphs, one for high prevention focus level and one for low prevention focus level. And on the vertical axis, we see the pick time it takes for the picker to pick in one aisle. So we are in the same aisle, and the model we use for that is a nested model per stopping node and per picker. So 2 levels of nesting. What we see is that if you have a human leading the robot, then we see that it takes less time than when the human is supporting the robot. So there's a lot more time when the robot is leading. It takes more time to pick. So the human leading leads to higher productivity, as we already saw. However, this is not so much true for pickers with a very high prevention focus. Pickers with a high prevention focus can basically mitigate this difference. So you might say people with prevention focus are not really affected by whether they lead or whether the robot leads, where people with a low prevention focus are seriously affected, and they have much longer pick times if the robot is leading. So this is also an interesting result. So yes, it appears to the personality, the behavioral trait of the worker appears to have an effect on the outcome. So you can also look at other variables compared to completely manual operation. Does it have an effect on task satisfaction? Yes, working with a robot leads to more satisfied people, an interesting result. And when the human is supporting the robot, it also leads to better self-esteem and positive ideas about the robot efficacy, so which is also interesting. Now I think, let me just skip that. Let me spend the last 5 minutes, if I may, Debjit.
Yeah, sure.
On the last system, I do this a bit quicker, I think, because this is really the robot system which is implemented now in a very rapid pace. This is probably the most successful type of cobot. These are cobots on which you can write. So you see them particularly in pallet warehouses. The other two robots are implemented in shelf type warehouses. This robot is particularly implemented in pallet type warehouses. Here are some pictures. So it's a truck. You can pick, in this case, multiple roll cages from multiple customers, boxes from pallets. So this is a grocery retail warehouse. But you can also use it in other environments, pallet warehouses. We drive to the locations like this, but we can also get off the location and start picking and walking. And when we start doing that, the robot will follow us. So it behaves like a truck when you sit on it, and it behaves like a robot when you get off. So that's interesting. And there's quite a few implementations recently of these types of trucks. And the reason is all the warehouses that already have conventional trucks can, with a small upgrade, now use these trucks, which are robots basically. So, and they are not much more expensive than the trucks they already have. So the investment is quite low. In fact, they lease them. So this is a relatively easy switch between the two systems, and that also explains their success, I think. The big question is, should the picker now walk or write between the locations, and when should the picker get off? So what I see is in practice is most pickers drive to these locations and they get off everywhere. And that might not be the best solution. So here are some examples. This is where the picker only walks in an optimal route. So we see the thin line, that's the truck, and we see the red line, that's the picker. So the picker walks to all the locations in the shortest path, and the robot follows the picker everywhere. So it is an extreme strategy, you might say. But you might also say, well, the picker drives on the robot or rides on the robot in optimal route and gets off everywhere. So here we get off, we pick it, we drop it in the roll cage, we get on the truck, we drive, get off the truck, pick, drop it off, get on the truck, etc. in an optimal route. Or we can have a mix. Sometimes we drive and sometimes we walk. So the first location we drive, then we start walking because the second location is close by. In the meantime, the robot follows us, we drop it off, we get on the truck, and here we drive. But here we walk. So we sometimes walk, sometimes drive. And that appears to be an interesting option with these type of trucks. So we can model this. This is the objective function. This is the total pick time per route. I'm not going to expend too much time on this now. If you look at the constraint, it's basically a TSP, but it's a bit different because sometimes you can drive and sometimes you walk. So you have to look at which locations do I drive to and which locations do I walk to. So we have two decision variables rather than one, which you would have in a conventional TSP. So this is the TSP formulation, standard TSP. You can implement this in Cplex and it solves. And it solves for not too large orders. So less than 50 picks, it's okay. Unfortunately, we were working with this particular store chain and they have huge orders. You have to think of hundreds of picks in one route sometimes. So really very large orders. And then of course, this doesn't work anymore. So we developed a dynamic programming model to solve also very large instances. And in fact, this problem is not NP hard, it's a polynomial. So the dynamic programming algorithm works quite efficiently. So we can solve really large instances using this DP. So the DP is you model it as a graph. So you model all the potential travel between locations that are feasible. and you model the ways you can move from one aisle here to the next aisle. And what you do then is, well, there's a limited number of options, and you just model all the transitions within the aisles, and you model the transitions between aisles. And then you look at the lowest cost transitions and you roll it up from the last aisle to the front aisle until you're back at the depot. That's sort of the idea in a nutshell. So it's based on the algorithm of Ratliff and Rosenthal, published in OR in 1983, and well, some update for multiple blocks by Roodbergen and myself in eJOR. So this is the transitions you can make, the state space, but let me just skip that and look at the results. So this is the result for a single block. Here you can see the benefits of the difference of optimal walking and optimal driving compared to the overall optimal strategy, which is a mix. So you see that optimal walking is up to 30% maximum gap, takes more time than optimal overall strategy. Optimal driving, this depends, of course, on the number of picks in the route. So more picks in the route, you see that optimal walking, optimal driving has a bigger impact, we see a larger improvement of the optimal overall strategy over optimal driving when the number of picks increases. But you see there's overall a benefit. So in nearly all situations, there is a big benefit of optimal combination, getting on and off. So this was the result for the company, but I just skipped that in view of time. Let me just wrap up. So the question is, are the bots going to take away the picker's role? Well, in view of all this, no, they will not. For the coming 10, 20 years, we'll see collaborative systems. So this will be the way that companies go ahead. So picker robots are here to come and here to stay, but we see that they will have to collaborate with robots. And the performance is not only determined by the type of system, but also how you control it, and also how you operate it together with people. And I think there's a lot of opportunity here for academic research. Anyway, this was what inspired me to do some research on this topic, and I'm going to do a couple of more things. Thank you very much.
Thank you, René, for all the fascinating parts of the speech. I would say. What was really exciting and interesting was the broad system was kind of similar, but how different methods can solve different kind of questions that you want to ask. In those lines, there are a few questions here. One question is by Zavi, and the question is all about, there are different methods of utilizing the robots. Like in some cases, robots follow human, in some cases, human follows the robot. So given they need different system configuration, I think you answered this, but the question is, which one do you expect to perform better in real time, especially when the number of small items are higher?
So this is about the
ergonomic picking with the Alexander's work, yeah.
Okay, so which system is going to perform better? So, and which are the options?
Whether the robot follows the human or the human follows the robot.
Okay, to be honest, I think here we see more errors when the human is in the lead. But when the human is in the lead, we see a higher productivity. I think, to be honest, there are ways to reduce the errors. So I would say let the human be in the lead. I think there's benefits of that system. And we can find ways to reduce the errors anyway. So yes, in our system, we found more errors, so it's more error prone, but you can get away of these errors. It's possible to do that. So for example, you can have check digits, extra checks, all kinds of things you can do if you really want to have errors low. So I would say, let the human be in the lead, higher productivity.
Thank you, René. And that this follow-up question is also from the first model that you presented. The question goes like this, is you discussed about dynamic switching between zone picking and no zone picking. Since peering model outputs helps in design decisions, is it okay to use this static decision together with more operational decision like dynamic switching?
Yes, we think that is possible. We even investigated such a policy, but I think there might be it might be hard to do that. It might be much more difficult to implement than just a dynamic switching policy. So a static policy is easy. Dynamic switching policy is possible, but if you want to do sometimes this, sometimes that, there are also some downsides to that. So it depends a bit on the exact implementation. So we had some really good alternative strategies, but we think they're not feasible. So in practice, that is. So the strategies we investigated are at least feasible strategies in practice. So I would have to know a bit more about to decide also on that aspect.
Sure. No, thank you, René. I think it was a very exciting talk, and you provide a fascinating line of research for potential future problems, and particularly how multiple methods can be useful to solve or analyze different questions for the same cobotic systems. I'm sure the participants here who attended your webinar benefited from your talk, and we hope that you'll be able to come and present your findings in future talks with us. Thank you all for joining, and thank you, René, for giving this talk. Thank you so much.